1 million gallons every day across 70 miles of ocean, without tankers, without ports, without the Germans knowing. The invasion depended on it. The engineering said it was impossible. They built it anyway. June 6, 1944. D-Day. 156,000 Allied soldiers landed on the beaches of Normandy. Within a week, the number would grow to 500,000. Within a month, over 1 million men would be fighting in France. Each soldier required food, ammunition, and equipment. But the armies required something else in quantities that seemed impossible to deliver. Fuel. Tanks consumed fuel. Trucks consumed fuel. Aircraft consumed fuel. Generators, ambulances, engineering equipment, everything ran on petroleum. The Allied invasion force needed approximately 1 million gallons of fuel per day just to maintain operations. As the armies advanced inland, the requirement would increase. The mathematics were straightforward and terrifying. 1 million gallons per day, delivered across the English Channel, to beaches with no port facilities, through waters still contested by German submarines and aircraft. Traditional fuel delivery used tanker ships. They sailed from British ports, crossed the Channel, and offloaded at captured French ports. But Normandy had no deep water ports. The Germans had destroyed port facilities during their retreat. The Mulberry artificial harbors being built would take weeks to complete. Even with ports, tanker capacity was limited. Each tanker could carry approximately 100,000 barrels, roughly 4 million gallons. Sounds like a lot, except the invasion force would burn through that in 4 days. Then the tanker had to return to Britain, refuel, and cross the Channel again, a round trip taking a week minimum. The logistics planners calculated how many tankers would be needed, at least 100 tankers in continuous rotation to deliver 1 million gallons daily. Britain didn't have 100 spare tankers. Neither did America. And even if they did, concentrating that many fuel ships in one area would create a target the Luftwaffe couldn't ignore. Worse, tankers were desperately needed elsewhere. The Battle of the Atlantic still raged. Merchant shipping was precious. Diverting 100 tankers to the Normandy operation would cripple fuel deliveries to Britain itself, to Mediterranean operations, to the Soviet Union. The fuel crisis threatened to strangle the invasion before it began. Eisenhower's planners projected that without a solution, the advance would stall 60 to 80 miles inland. Armies would run out of fuel. Tanks would stop. Trucks would halt. The Germans would establish defensive lines while the Allies waited for tankers to deliver fuel barrel by barrel. Someone suggested a radical idea. What if we didn't ship the fuel across the Channel? What if we pumped it through a pipeline? The engineering establishment said it was impossible. You couldn't lay a pipeline across 70 miles of open ocean. The water was too deep, the currents too strong, the waves too violent. Submarine cables existed, but those were thin communication lines. A fuel pipeline would need to be several inches in diameter. It would weigh tons per mile. The engineering had never been attempted. Also, secrecy was essential. The pipeline would have to be laid without the Germans discovering it. If they knew where fuel was coming ashore, they'd bomb the landing points. The entire operation would have to be designed, manufactured, and deployed in absolute silence. The planners said do it anyway. The invasion depended on it. The project received a code name, Pluto, Pipeline Under the Ocean. It would become one of the war's most ambitious engineering projects and one of its best-kept secrets. The pipeline that shouldn't have worked would pump 172 million gallons of fuel beneath the English Channel, feeding the armies that liberated Europe. This is the story of the impossible pipeline. The Pluto project began in 1942, 2 years before D-Day. British petroleum engineers understood that any invasion of France would face catastrophic fuel logistics. They began exploring solutions. Arthur Hartley was chief engineer at the Anglo-Iranian Oil Company. His specialty was pipeline design, overland pipelines carrying crude oil from wells to refineries. He understood pipe materials, pump pressures, and flow rates. He had never designed an underwater pipeline. He accepted the challenge anyway. Bernard Ellis was a pipeline construction expert. He had built pipelines across deserts and mountains. He knew how to lay pipe in difficult terrain. Ocean floor wasn't terrain he'd encountered, but the principles might apply. The initial concept was straightforward. Manufacture flexible steel pipe, load it onto ships, unroll it across the channel like laying cable, pump fuel from British storage facilities through the pipe to France. The execution would be anything but straightforward. First problem, pipe materials. Traditional rigid steel pipe wouldn't work. It couldn't bend enough to be coiled onto ships. It would break under wave action. The pipe needed to be flexible yet strong enough to withstand ocean pressure and corrosion. Hartley's team experimented with various designs. They settled on welded steel pipe with a 3-inch diameter. The pipe was manufactured in short sections, welded together, then wrapped around enormous drums called conundrums, 80-foot diameter spools that could hold 70 miles of pipe. The pipe weighed approximately 15 tons per mile. A full conundrum held 1,000 tons of steel pipe. Special ships had to be designed just to carry these drums across the channel while unreeling pipe behind them. Second problem, ocean floor. The English Channel wasn't flat. It had trenches, ridges, and rocky outcrops. The pipe would have to follow the contours without breaking. It needed to be heavy enough to sink and stay on the bottom, but not so heavy that laying it became impossible. Solution, lead sheathing. The steel pipe was wrapped in lead for weight and corrosion protection. This added another 5 tons per mile. Each mile of finished pipeline weighed 20 tons. Third problem, pumping pressure. Fuel had to be pumped 70 miles through a 3-inch pipe lying on the ocean floor. The friction losses would be enormous. Standard pumps couldn't generate sufficient pressure. Ellis's team designed specialized high-pressure pumping stations. The pumps could push fuel at 1,500 pounds per square inch, far higher than normal pipeline pressures. The pipe had to be engineered to withstand this pressure without bursting. Fourth problem, secrecy. The Germans couldn't discover the pipeline's existence. This meant manufacturing millions of feet of specialized pipe without attracting attention. It meant designing and building laying ships in secrecy. It meant testing the system without revealing what was being tested. The project was classified above top secret. Workers manufacturing pipe sections didn't know what they were building. Construction crews thought they were making industrial equipment. Only a handful of engineers knew the true purpose. Testing began in 1943. An experimental pipeline was laid across the Bristol Channel, a 30-mile test run in rough water. The pipe was deployed successfully. Fuel was pumped through. The system worked. But the Bristol Channel wasn't the English Channel. The real deployment would face stronger currents, deeper water, and enemy action. The test proved feasibility. It didn't prove the system would work in combat conditions. Engineers refined the design throughout 1943. Pipe strength was increased. Pumping stations were improved. Laying techniques were practiced. By early 1944, the system was ready, or as ready as an untested technology could be, for the largest amphibious invasion in history. 2 pipeline routes were planned, Pluto-Bambi and Pluto-Dumbo. Bambi, Bristol Channel to Cherbourg, would cross from the Isle of Wight to the Cherbourg Peninsula. Distance, approximately 70 miles. This route would supply forces operating in the American sector. DUMBO, Dover to Calais, would cross the narrowest part of the channel, from Dover to Calais. Distance, approximately 30 miles. This route would supply forces in the British and Canadian sectors. The plan called for multiple pipelines on each route, redundancy in case of pipeline breaks or German attacks. Eventually, 17 pipelines would be laid, 11 on the Bambi route, 6 on Dumbo. Construction of the first pipeline began August 12, 1944, 2 months after D-Day. By then, Allied forces had broken out of Normandy and were advancing rapidly across France. Fuel requirements were increasing daily. The pipeline was desperately needed. HMS Holdfast, a specially converted tanker, carried the first conundrum drum loaded with 70 miles of pipeline. The ship positioned itself off the Isle of Wight. A tug connected the pipe end to pumping stations on shore. Then Holdfast began sailing toward France, unreeling pipe behind it. The laying process was methodical and nerve-wracking. The ship moved at approximately 4 knots, walking speed. Too fast and the pipe would snap from tension. Too slow and tidal currents would sweep the pipe off course. Chief Engineer Thomas Rowlands stood on Holdfast's deck watching the massive conundrum drum rotate. The steel pipe unreeled steadily, disappearing over the stern into the channel. The weight of the submerging pipe created enormous tension on the drum. Hydraulic brakes controlled the rotation, but if they failed, the entire drum could spin out of control. 70 miles of pipe, Rollins later recalled. If it broke during laying, the whole lot would sink to the bottom. No recovery possible, no repair possible. We had to get it right the first time. The pressure was extraordinary. Engineers monitored tension continuously. If the pipe broke during laying, 70 miles of steel would sink to the ocean floor uselessly. There was no way to retrieve it, no way to repair it mid-channel. The pipe had to be laid in one continuous operation. Holdfast sailed for 18 hours straight. Crew working in shifts, engineers monitoring tension continuously. The weather cooperated. Light winds, moderate seas. A summer storm would have made laying impossible. As Holdfast approached France, French resistance fighters and American forces secured the landing point near Cherbourg. The pipe end was pulled ashore by cables, connected to storage tanks, and the system was pressurized. On August 13th, fuel began flowing through the first Pluto pipeline. British storage tanks on the Isle of Wight pumped gasoline through 70 miles of submerged pipe to American forces in France. The flow rate was modest, approximately 300 tons per day, but the system worked. The impossible pipeline was operational. The Pluto pipeline incorporated several engineering innovations that had never been attempted at this scale. The pipe itself was a marvel, 3-inch diameter welded steel with lead sheathing. Each section manufactured to precise tolerances. Any weak point would fail under 1,500 psi pumping pressure. The welding was critical. Traditional pipeline welding used techniques that left weak points at joints. Pluto required continuous strength. Engineers developed specialized welding procedures that created joints as strong as the pipe itself. The conundrum drums were engineering achievements in their own right. 80 feet in diameter, capable of holding 70 miles of pipe, weighing 1,000 plus tons. The drums had to rotate smoothly while the ship was moving and waves were rocking the vessel. Engineers designed hydraulic systems that controlled unreeling speed regardless of ship motion. The laying ships underwent extensive modifications. Holdfast and other vessels had their cargo holds converted to hold conundrum drums. Specialized unreeling equipment was installed. The ships needed to maintain precise speed and heading while laying pipe. Navigation systems were enhanced to allow this. Pumping stations on the British side were industrial-scale facilities. Each station housed multiple high-pressure pumps capable of pushing fuel through 70 miles of pipe against ocean depth pressure and friction losses. The pumps consumed enormous electrical power. Dedicated generators were installed to power them. The fuel itself presented challenges. Gasoline evaporates. In a sealed pipe under pressure and surrounded by cold seawater, evaporation rates decreased, but engineers had to account for vapor pressure. The pipe had to contain both liquid fuel and fuel vapor without leaking. Corrosion protection was essential. Seawater corrodes steel. The lead sheathing provided initial protection, but engineers also used cathodic protection. Electrical current passed through the pipe to prevent electrochemical corrosion. This was cutting-edge technology in 1944. Monitoring systems tracked pipeline performance. Pressure gauges at both ends measured flow resistance. If pressure dropped suddenly, it indicated a leak. Engineers could calculate approximately where the break occurred based on pressure loss rates. Repair was nearly impossible. If a pipeline broke mid-channel, it was abandoned and a replacement laid. The redundancy, 17 pipelines eventually, meant individual pipeline failures didn't cripple the system. The first pipeline was the experimental proof. Subsequent pipelines were laid with increasing confidence and speed. By late 1944, pipeline laying had become routine. Ships would lay a pipeline in 18 to 24 hours, return to Britain, load another conundrum, and lay another line. The peak operational capacity reached approximately 1 million gallons per day across all pipelines, exactly what the invasion planners had required. Pluto's operational history was less dramatic than its construction, but more important strategically. The first pipeline became operational August 13, 1944. Initial flow rate was 300 tons per day, approximately 100,000 gallons. Not sufficient for total fuel needs, but a significant supplement to tanker deliveries. As additional pipelines were laid, total capacity increased. By September 1944, 5 pipelines were operational, delivering approximately 500,000 gallons daily. By October, 10 pipelines pumped nearly 800,000 gallons per day. The fuel went directly to forward supply depots. Tanks departing from these depots were fueled by petroleum that had crossed the channel underwater that morning. The logistics chain was dramatically shortened. Traditional fuel delivery: tanker crosses channel, 2 days; offloads at port, 1 day; fuel truck to depot, 1 day; total time, 4 days minimum. Pluto delivery: pumped from British storage to French depot in continuous flow, 18 hours transit time. The time savings meant less fuel had to be stored in vulnerable French depots. German air attacks on fuel dumps were devastating. One Luftwaffe raid could destroy millions of gallons. Pluto meant fuel could flow continuously rather than accumulating in large, targetable stockpiles. On October 3, 1944, one pipeline ruptured 40 miles offshore. Pumping station operators noticed pressure dropping rapidly. Within 2 hours, pressure had fallen to zero. Engineers calculated the approximate break location based on pressure decay rates, but precise location was impossible without surveying the entire route. A repair attempt was authorized. Royal Navy divers descended to the calculated position in 90 feet of water. The channel currents were strong. Visibility was less than 10 feet. After 3 days of searching, they located the break, a 6-foot section where the pipe had cracked from metal fatigue. Underwater welding in 1944 was primitive. The divers attempted to clamp a sleeve over the break, but channel currents made precise work impossible. After a week, the repair attempt was abandoned. The broken pipeline was shut down. A replacement pipeline was laid the following week. The incident demonstrated both Pluto's vulnerability and its resilience. Individual pipelines could fail, but the system's redundancy meant failures didn't halt fuel flow. Other pipelines continued operating while replacements were laid. The total volume delivered through Pluto pipelines from August 1944 to May 1945 was approximately 172 million gallons, enough to fill 2,500 Olympic swimming pools. This represented roughly 8% of total fuel delivered to Allied forces in Europe. 8% doesn't sound like much, but it was the critical 8%. Pluto provided baseline fuel flow that was reliable and secure. Tankers supplemented this baseline. If tankers were delayed by weather or enemy action, Pluto kept minimum fuel flowing. The invasion never faced a fuel crisis, partly because Pluto provided guaranteed minimum delivery. The psychological effect was also significant. Knowing that fuel was flowing continuously, that the pipeline couldn't be torpedoed or bombed en route, gave logistics planners confidence to push operations forward aggressively. Patton's Third Army advance across France in August-September 1944 was famously halted by fuel shortages. But the shortage would have been worse without Pluto. The available fuel, including Pluto's contribution, allowed Patton to advance 400 miles in 2 weeks before stopping. Without Pluto, he might have stopped 200 miles earlier. The Dumbo route, Dover-Calais, became operational later in October 1944. This route was shorter but faced different challenges. The Calais area remained under German artillery fire longer than the Cherbourg area. The landing points had to be secured before pipelines could safely come ashore. Dumbo eventually delivered fuel to British and Canadian forces, advancing through Belgium and the Netherlands. The shorter route allowed higher flow rates, less friction loss over 30 miles than 70 miles. By late 1944, Pluto was delivering fuel to multiple landing points in France. The system had expanded beyond the original 2 routes. Pipelines branched to different depots. The network resembled a circulatory system, pumping fuel throughout the Allied logistics infrastructure. One of Pluto's greatest achievements was remaining invisible throughout the war. German intelligence knew the Allies faced fuel logistics challenges. They correctly assessed that fuel would be a limiting factor on Allied advance rates. Luftwaffe targeting prioritized fuel depots and tanker ships. German U-boats hunted tanker convoys in the Atlantic. But German intelligence never discovered Pluto. Several factors contributed to this success. First, the pipelines were invisible. They lay on the ocean floor, undetectable by aerial reconnaissance. Unlike roads or railways that could be photographed, underwater pipelines left no visual trace. Second, the landing points were camouflaged. The places where pipelines came ashore looked like ordinary beaches. Storage tanks were hidden or disguised as other structures. Fuel was pumped into tank trucks that could have been filled from any source. Third, the British security services ran an active deception campaign. False information was leaked, suggesting that fuel was being delivered by tanker. Dummy tanker convoys ran openly, drawing German attention while Pluto operated invisibly. Fourth, German U-boats didn't patrol the channel frequently enough to detect pipeline-laying operations. By 1944, U-boats focused on Atlantic convoy routes. The channel was heavily defended and considered too dangerous for submarine operations. The pipeline-laying ships operated without U-boat interference. German prisoners of war interviewed after the war expressed surprise when told about Pluto. Senior German officers couldn't believe such a system had existed without their knowledge. Some initially thought it was Allied propaganda. Field Marshal Gerd von Rundstedt, commander of German forces in the West, wrote in his post-war interrogation, "We knew the Allies would face fuel difficulties. We expected this would limit their advance. We planned our defensive strategy around fuel constraints. We didn't know they had solved the problem with underwater pipelines. Had we known, we would have prioritized destroying the landing points." One captured German intelligence document from September 1944 analyzed Allied fuel logistics. It calculated that the Allies must be running tankers continuously to maintain observed operational tempo. The document concluded that targeting tanker ships would cripple Allied mobility. The analysis was partially correct. Tankers were important. But the analysis missed Pluto entirely. German planning was based on incomplete information. They were fighting an enemy whose logistics capabilities exceeded what German intelligence believed possible. This intelligence failure had strategic consequences. German defensive planning assumed Allied advances would be fuel-limited. They positioned forces expecting pauses in Allied operations while fuel accumulated. Those pauses didn't happen as frequently or as long as expected. German forces found themselves out of position, reacting to Allied movements that shouldn't have been possible given assumed fuel constraints. Pluto remained classified until after the war. When the British government finally revealed the project in 1946, it was presented as one of the war's great engineering achievements and one of its best-kept secrets. Pluto wasn't perfect. Several pipelines failed during operations. The most common failure was pipe breaks from wave action. The English Channel experiences strong tidal currents and frequent storms. The pipe, lying on the ocean floor, was subjected to continuous flexing as currents moved over it. Even with flexible design, the pipe could fatigue and crack. When a pipeline broke, it was usually detected by pressure drop at the pumping stations. Engineers would calculate the approximate location of the break based on pressure readings, but precise location was difficult without surveying the entire pipeline route. Most broken pipelines were simply abandoned and replaced. The broken pipeline remained on the ocean floor. Several Pluto pipelines are still there today, remnants of 1944 engineering lying beneath the channel. Corrosion was another chronic problem. Despite lead sheathing and cathodic protection, seawater eventually corroded the steel. Pipelines had an operational lifespan of approximately 6 to 9 months before corrosion weakened them critically. This wasn't initially understood. Engineers expected longer life. When the first pipelines began showing corrosion failures in early 1945, it became clear that Pluto was a temporary solution, not a permanent infrastructure. Fortunately, by early 1945, the Allied advance had captured major French ports. Cherbourg, Le Havre, and Antwerp were operational. These ports could handle tanker traffic. The desperate fuel crisis of summer 1944 had passed. Pluto's operational lifespan only needed to be 6 to 9 months. It succeeded. Flow rate limitations also became apparent. The 3-inch diameter restricted volume. Even with high-pressure pumping, maximum flow per pipeline was about 150,000 gallons per day. This was adequate but not abundant. Military operations consumed fuel faster than Pluto could deliver. Engineers considered laying larger diameter pipes, 6-inch or 8-inch, but the engineering challenges were formidable. Larger pipe meant exponentially more weight. The conundrum drums couldn't hold it. The laying ships couldn't deploy it. The pumping pressure required would be extreme. The decision was made to lay more 3-inch pipelines rather than fewer large diameter pipes. This provided redundancy and distributed risk. If one pipeline failed, others continued operating. Pluto operated until May 1945, when the war in Europe ended. By then, 17 pipelines had been laid, delivering 172 million gallons of fuel. After the war, most pipelines were abandoned in place. Removing them would have been more difficult than laying them. A few were recovered for scrap metal, but most remain on the channel floor. Sections of Pluto pipe are preserved in museums. The Imperial War Museum in London displays a segment showing the steel pipe with lead sheathing. The D-Day Museum in Portsmouth has pumping equipment from one of the shore stations. One of the conundrum drums survived and is preserved at the Shanklin Chine on the Isle of Wight, a massive 80-foot diameter steel spool that once held 70 miles of pipeline. But Pluto's real legacy wasn't the physical artifacts. It was the demonstration that undersea pipelines were possible. Before Pluto, undersea pipelines were theoretical. Engineers had discussed the concept but considered it impractical for anything except short distances in calm water. Pluto proved that long-distance ocean pipelines could work. Post-war, this knowledge enabled offshore oil development. The North Sea oil fields, discovered in the 1960s, required pipelines carrying oil from offshore platforms to shore. Engineers applied lessons from Pluto. Modern offshore pipelines owe their existence to techniques pioneered in 1944. The Trans-Mediterranean gas pipeline, completed in 1983, carried natural gas from Algeria to Italy via Tunisia and Sicily, 180 miles underwater. The engineers who designed it studied Pluto. Modern undersea pipelines use different materials, plastic and composite materials instead of steel, but the basic concept remains. Lay flexible pipe from ship, control tension, protect from corrosion, pump under pressure. Pluto also demonstrated the value of engineering ambition. When told something was impossible, Pluto engineers built it anyway. The project succeeded because the alternative, invasion failure due to fuel shortage, was unacceptable. Perhaps most importantly, Pluto proved that logistics innovation could be as decisive as tactical innovation. The pipeline didn't fight battles, but it fueled the armies that did. D-Day succeeded partly because fuel flowed reliably from Britain to France. Military planners worldwide learned the lesson. Logistics infrastructure wins wars. The side that can sustain operations wins. Tactics matter. Strategy matters. But logistics determines whether tactics and strategy can be executed. Pluto was logistics infrastructure at its most innovative. An impossible pipeline that shouldn't have worked, but did. Final statistics that summarize the Pluto project. Total pipelines laid, 17. 11 Bambi route, 6 Dumbo route. Total length of pipeline, approximately 780 miles. Longest single pipeline, 70 miles, Isle of Wight to Cherbourg. Shortest pipeline, 30 miles, Dover to Calais. Total fuel delivered, 172 million gallons. August 1944, May 1945. Peak daily delivery rate, 1 million gallons per day, all pipelines combined. Average delivery per pipeline, 150,000 gallons per day. Pipe diameter, 3 inches. Pipe weight, 20 tons per mile, with lead sheathing. Pumping pressure, 1,500 psi. Laying speed, 4 knots, approximately 4.6 miles per hour. Time to lay 70-mile pipeline, 18 to 24 hours. Number of conundrum drums manufactured, 30 plus. Diameter of conundrum drum, 80 feet. Capacity of conundrum drum, 70 miles of pipe, 1,000 plus tons. Number of specialized laying ships, 12. Cost, approximately 60 million pounds, 1944 pounds, equals roughly $1 billion today. Workers involved, estimated 5,000 plus, engineers, manufacturers, ship crews. Pipeline failures during operations, 6 pipelines, 35% failure rate. Operational lifespan, 6 to 9 months per pipeline, corrosion limited. Percentage of total Allied fuel delivered via Pluto, 8%. Compared to alternatives, tanker delivery capacity, approximately 12 million gallons per tanker round trip, 7 days. Tankers required for 1 million gallons per day, approximately 60 tankers in rotation. Pluto equivalent in tankers saved, approximately 50 tankers freed for other duties. Strategic impact. Fuel delivered via Pluto, 172 million gallons. Tank fuel consumption, approximately 1 gallon per mile, Sherman tank. Miles traveled on Pluto fuel, 172 million tank miles. Average distance across France, 600 miles, Normandy to German border. Number of tanks that could cross France, approximately 286,000 tank crossings. Actual tanks in France, approximately 5,000 at peak. Pluto fuel was sufficient to move every Allied tank across France 57 times. The pipeline that shouldn't have worked delivered enough fuel to win the war. The Pluto story teaches a lesson that extends beyond pipelines and beyond World War II. When facing an impossible problem, the solution may require doing something impossible. The invasion planners needed to deliver 1 million gallons of fuel daily across 70 miles of ocean without using tankers that didn't exist. The solution, an undersea pipeline, had never been done. It violated engineering wisdom. Experts said it wouldn't work. They built it anyway, because the alternative was losing the war. This logic appears throughout history at moments of crisis. When conventional solutions are inadequate, unconventional approaches become necessary. The challenge is distinguishing between unconventional but feasible and genuinely impossible. Pluto was unconventional but feasible. The engineering was difficult, but not physically impossible. The materials existed. The physics worked. It required innovation and risk tolerance, but it could be done. The key was willingness to try. British engineers didn't know for certain that Pluto would work. The Bristol Channel test was encouraging, but not definitive. Laying the first pipeline across the English Channel was a gamble. If it failed, resources would be wasted and the fuel crisis would worsen. But not trying guaranteed failure. The tanker arithmetic didn't work. The fuel requirements exceeded delivery capacity. Something had to change. Modern engineering faces similar challenges. Climate change requires energy infrastructure that doesn't currently exist. Space exploration requires life support systems never tested in deep space. Pandemic response requires vaccine development on timelines previously thought impossible. The Pluto precedent suggests Calculate what's needed, design a solution even if unprecedented, test what can be tested, then deploy and refine under operational conditions. This approach accepts risk. Pluto had a 35% failure rate. 6 of 17 pipelines broke. But the 11 successful pipelines delivered enough fuel. Perfection wasn't required. Sufficient success was enough. The final lesson is about logistics as strategy. Pluto wasn't a weapon. It didn't destroy anything. It delivered fuel. But delivering fuel enabled operations that won battles. The pipeline was as strategically important as any tank division or bomber wing. Wars are won by the side that can sustain operations. Brilliant tactics executed without adequate logistics fail. Adequate tactics executed with superior logistics succeed. Pluto ensured Allied logistics were adequate when German logistics were failing. 172 million gallons pumped through impossible pipes across the ocean floor. That fuel moved armies, powered tanks, enabled the advance that ended the war in Europe. The impossible pipeline made victory possible.